Hello all and welcome to Lab 5. This one I chose to do energy and restitution. The purpose of this lab was to examine how imperfect elastic collision affects vertical movement, in essence a bouncing ball. Some of the key terms that we'll need to know are that we'll be using the GlowScript computational model to predict some of this stuff. We'll need to know about potential and kinetic energy. We'll need to know about restitution, or the restitution coefficient, and the velocity and position update formula. The preview is that we found that we can estimate the restitution of a ball given data, and we can estimate how high up the ball will bounce. So the equation for restitution is our velocity after the ball has collided with the ground divided by the velocity directly before the ball collided with the ground. Our kinetic energy formula is 1/2 mv squared. Our potential energy formula is mgh, and then if we use these to find the height, we can find that the height of a bouncing ball will be the velocity directly before it bounced squared divided by 2 times the gravity coefficient. The reasoning was that we'll use the GlowScript to compare the predicted results to the actual results, and we'll find where the ball's velocity changes from negative to positive, or where it bounces, and then divide the final velocity by the initial velocity, and do this for each bounce to find the average coefficient of restitution. We can also estimate a bounce using the height of height is equal to v squared divided by 2g. The systems and the surroundings. The system for this is going to be the mass slash the ball, and also the earth. And the surroundings is going to be the air, which is causing drag and a loss of energy due to work from friction. The initial conditions are there's no velocity in the x or y direction, and it is the ball is 0.015 kilograms because it is a foam ball. The experiment itself was I dropped a ball vertically, and I made sure the recording device was stable. I waited until the ball stopped bouncing to stop the video, and I tried my best not to have the ball move in the x or z directions. If it moves in the z direction, then each of the bounces will seem a lot larger than they actually are, and if it moves in the x direction, then I might not catch each of the bounces as it goes. Finding the coefficient of restitution is very easy. This is just one example. So I did find the average to be 0.736. This is one example that gave me 0.736. It's just the velocity after the ball bounces divided by the velocity before the ball bounces. It is difficult to find a good set of data to compare this to because you want to have as many frames of data as possible, and a lot of phones won't capture that. So you want to find the velocities that are an equal distance from when the ball bounced. The major portions of the code that I changed, this was very similar to the code from Lab 2, was that if the ball's velocity was, not equal to, if it was just greater than 0, then I would use the normal velocity update formula. However, if the ball was below 0, or was at 0, which is where the ground is, then I would use the restitution, which we found here. I would multiply that by -1, and then I would multiply the ball's velocity by that. So if the ball's velocity was 1, it would then become, if the ball's velocity was -1 because it's heading downwards, then it would become a positive 0.736. So it would reverse, and then it would scale. And then I would also put the position of the ball a little bit above 0. That way it doesn't trigger repeatedly. If it went all the way down and then started to go back up, then it might multiply this a bunch, and then it would just fizzle out down here under the ground, which is not what we would want. We can also estimate using the energy, as I did before, where one data point was the velocity directly before the bounce, was found to be this, gravity, the height formula, and then this is what we found, what our next highest bounce should be, which the actual next highest bounce was this, and from that we can see that we only had a 12.48% error, and this doesn't include drag, so this is actually a very accurate representation. Here are some of the graphs of similarities and difference. This is using the restitution. I did not use energy for this. So we can see that this obviously has more bounces than this does. However, the peaks and the troughs are consistent after this first one. This is largely due to the fact that this GlowScript data didn't include drag. There was a lot of errors that happened if it did include drag. There was a different number of bounces. A lot of the errors are from the tracker video, where you can have misclicks, but the ball also ended up moving in the Z direction, so there was that error. There was also the parallax error of the phone being at different heights, so it saw the phone being at one height far away, so it saw the ball at different heights. And then there was also the area from the video kind of being tilted. If the ball was inelastic, then there would be no bounce, it would just stick to the floor. If it was perfectly elastic, then it would eventually stop moving because of drag, but it would take a lot longer to reach there. And then here's my video. Thank you.